Okay, cool. So this is intro to binary exploitation. Um, it's a kind of hard topic to start for the first time. Um, but we'll just jump right in. I'm not really going to assume any prerequisite knowledge. I'll talk a little bit about things that may require prerequisite knowledge, but in the end, it's not very important. Um, Yeah, like essentially, if you get lost halfway through the talk, just like don't worry about it. The end of the talk shouldn't really rely on prerequisite knowledge. Cool. So I'll start with kind of a review of some very general computer architecture stuff, and then we'll get into the actual like binary exploitation stuff. Um, the architectural stuff, though, should be um, pretty standard if you've ever taken a class in computer architecture. Um, this is the part where if you get lost during the architecture review, like don't worry about it. It doesn't really matter. Um, yeah. So um, I guess like the first thing we'll talk about is just registers in general. So you have a bunch of registers. Um, they only store integer data. There's only 16 of them. They have special purposes. So there's really no way that you can store any sort of meaningful data in your registers. So what we do instead is we store all of the meaningful data in memory. So memory is it's essentially your RAM, and you can really just think of it as a big byte array. It's just a huge array that you can read and write bytes to. Um, Pointers are just like indices into this array, and I may switch up and say addresses instead of pointers. They're the same thing. It's just a number that associates some location in memory. Um, so yeah, like just kind of keep this model in mind. Like most of the stuff that your program uses is stored in memory. Um, the actual code itself that the program is running is also stored in memory. And then there's a couple registers that are pointers into memory that are fairly important. So RIP is the instruction pointer, which um, essentially just keeps track of which instruction should be executed next. So RIP is literally just like what code is executing at this specific moment in time. And the other two registers that are pointers into memory are RBP and RSP, and these are used to keep track of function local variables. And I'll talk more about that in just a second. Okay, so that's kind of a very brief overview of uh, kind of the only computer architecture knowledge that is required to understand exactly what's going on here. Um, if it didn't, if that was like a confusing few minutes, like you don't know what I'm talking about, don't worry about it. It doesn't matter. Um, cool. So going on, and we'll now talk about how functions are kind of implemented in C and I guess in assembly as well. Um, and there's a few reasons that we really care about this. Um, but the main reason is that when you have a function and you call that function has to store its local variables somewhere. And the way that this is done is the function is given like a memory region uh, in a place called the program stack, and the function just stores its variables in this memory region that it was given. Um, so yeah, this is essentially what it looks like. Like your function is given some memory, and it just puts its local variables in this area of memory that it's given. And this is where I was talking about RBP and RSP. So RBP and RSP keep track of like the beginning and end of this memory region that the function is allowed to put its local variables in. So you can see this picture right here. If there's a function called foo that is currently running, um, it has the RBP and RSP kind of aligned to where this memory live, or where this region lives in memory, and then it just puts its local variables between them. So um, how like obviously you're going to have multiple function calls at the same time, right? So say you have a function foo that calls a function bar, right? You need to keep track of the local variables for both of those functions at the same time, because like when bar finishes running, it needs to go back to foo, and foo needs to have its local variables still. So what we do is we just make a stack of these stack frames, and this is where the words like program stack come from. We just have like we literally just append them on top of each other in memory. Um, so if you have like foo calls bar, the picture looks like this picture here on the right, um, where foo has its local variables, and then there's a stack frame for bar right above that on the stack, and bar's local variables live there. Um, and it might be worth noting that the bottom of the stack is at a very high address, which is somewhat counterintuitive. You would think that the top of the stack would be like the highest address of the stack, but it's backwards. The top of the stack is actually the lowest address on the stack. Um, that also doesn't really matter. It's just kind of an interesting side note if you ever run into issues. Okay, so you may have noticed on these pictures that I have some like random things that I haven't talked about. There's like this saved RBP and this return address in these stack frames, and I didn't mention what those are or why they're there. Um, and those are just metadata about the calling function. So this saved RBP is exactly what you would think it is. It's the saved RBP for the previous stack frame. So um, essentially this like when you call another function, you need to keep track of where the stack frame for that caller function is, because you're going to now be keeping track of the stack frame of the callee function. So the saved RBP value just tells us where the previous stack frame used to be. And then we have this return address. And this return address just tells us, hey, when this function's finished executing, you should like continue executing here. So you can see this picture on here where the bar stack frame has this return address, and the return address is pointing into foo, and it would be pointing to this dot 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 right here. So foo would call bar, bar would like finish running, and it would return. And then when bar has finished running, you would expect it to like pick up inside of foo exactly where it left off. And that's really all that these things do. And we just stick them between stack frames, so we just have this metadata between stack frames. And really, if you get anything out of this talk, it should be like understanding this picture right here. Like this picture is probably the basis of almost all binary exploitation attacks. I would just say like study this picture in depth until you understand exactly like what it does, and then you will be able to figure out binary exploitation without me even telling you how to do it. Um, but so I will tell you how to do it though. um, but yeah, just keep in mind that there's this metadata that is right next to your local variables. It seems like an interesting place to put it, because functions often write to their local variables. So maybe we could try writing to the metadata instead. Okay, so now we're going to talk a little bit about some assembly instructions. There's a lot of assembly instructions, but we were only we only really care about 4 of them, and these 4 of them are the ones that interact with the program stack. Um, you may have noticed by this point in the talk that I'm really only talking about the program stack, and that's probably because the program stack is really the only thing that's useful in like easy to medium binary exploitation tasks. Like all you need to understand is the program stack. So um, we have our first instruction is just the push instruction, which literally just pushes a register value onto the top of the stack. Um, it does exactly what you would think it does. It just like puts the value on the top of the stack and then increases the size of the stack by 8 bytes. Similarly, we have the pop instruction, which is just the opposite of the push instruction. Um, these don't really matter for us, but what does matter for us is the call instruction, which kind of uses the push in a way. So what the call instruction does is it calls a function and it sets up this stack frame metadata. So what it does is it pushes the return address onto the stack and then jumps to whatever function you're calling. Um, and then we have the ret instruction, which is the opposite in the same way that pop was the opposite of push. So it just um, like pops the stack frame metadata off of the stack and then goes to that address. It does exactly the opposite of call. Okay, so now that we have all of these things in mind, we are able to talk about how we actually use these things to exploit a program. And the whole reason that things like this work is because C is really stupid and C does not care about um, like bounds checking when accessing arrays or like literally anything. You can do whatever you want in C, and that makes it really easy to write bugs into your code. So suppose we have like this piece of code right here that just allocates a string and then reads into that string. Um, so the reason that this is bad is because we're using this function getS, and if we were to look at the like C manual page for getS, we see that it says like never use this function. It's impossible to tell without knowing the data in advance how many characters getS will read. Um, getS will continue to store characters past the end of the buffer. It is extremely dangerous to use and has been used to break computer security. So essentially what this is telling us is that if we are to read a string with getS into our character array, it's not going to check that we only read like the length of our array. We can read as many bytes as we want and potentially overwrite random stuff in memory. So here's what this would kind of look like in assembly. So we allocate a character array size 64 and we call getS on it. So what this is doing in the assembly is those first 3 instructions are setting up the stack frame. So the first one is pushing that saved RBP value onto into the stack frame. This is like setting up some of that stack metadata. Um, and then the third instruction is actually allocating the stack frame. So our stack frame has size 64. We load the address of the like bottom of the stack frame, and then we pass that into getS. So um, essentially what this is doing is it's just allocating 64 bytes in memory for a stack frame and then allowing us to write into those 64 bytes. And this is kind of what this would look like. So you can see like if X is our string, then we have X0 through X63 um, in our stack frame, and then immediately afterwards we have our saved RBP and our return address. So we have this metadata right after. And if we remember what getS said, it said if we're to read 65 bytes, for example, then we will start overriding the saved RBP value. And maybe if we read like 80 bytes, we could overwrite the return address as well. So this is interesting because if we overwrite the return address, we can redirect the program's execution. Because remember, when the function returns, the program just jumps to whatever the return address says. So if we overwrite the return address with like a bunch of zeros, when the function returns, it's going to try to return to like a bunch of zeros, the memory address, a bunch of zeros, and then assuming that the address a bunch of zeros is not valid code, we will then crash the program. And the whole idea of binary exploitation is, what if we like pointed it to valid code? What can we do? How can we get the program to do interesting things? So this is exactly what I mean when I say this. So um, we have this our stack frame, and we just overflow the buffer. We overwrite the saved RBP value, and we overwrite the return address with some number. Let's suppose there's like a get flag function in our binary. We could overwrite the return address with the address of get flag, and then when this function returns, instead of returning to uh, the actual caller, will return to get flag, and the get flag function will then run. Um, so that sounds great, but what if we don't have like a get flag function, or a single address that's going to give us the flag when we jump to that address? Um, and the idea here is that we can chain these we can kind of chain this attack. So say we have 3 functions that we want to call in a row. We can just keep overwriting data in the stack until we have this kind of layout where it's function 2, and then function 3. And then essentially what's going to happen here is, when we return from uh, this, I think it was called like user input. When we return from the user input function, we will go to function 1, and then when we return from function 1, it's going to then return to function 2, and then when we return from function 2, we will then call function 3. So essentially what this allows us to do is run code, like just run functions sequentially, um, by kind of just chaining them together, uh, uh, like on the stack in this way. And I would say, if you're going to remember a picture from this talk, it would be this picture. This picture is um, kind of like the heart of most stack-based binary exploitation um, tasks. And this is called a ROP chain. That's what this kind of chain of functions is called. So cool. We're able to control the instruction pointer and call different functions, but what functions do we want to call? Like, okay, easy problems in CTFs might have a function called get flag, but I can guarantee you that any sort of like real world program isn't going to have a function that dumps like all their user data um, just onto like standard out. That would be stupid, right? Like no program's going to do that. So what we can do instead is we can call libc built-in functions. So like system, or read, or write, or um, different functions like that. And if we are able to call those functions with specific arguments in a specific order, we may be able to like leak some secret file back to ourselves, or open a shell, and then just be able to like interact with the program as if we were interacting with our own computer's terminal. Um, so you may notice that in order to call these libc built-in functions like system, we need to be able to control the parameters that are handed to this function. Because obviously, if you just call system with like completely invalid arguments, then system is going to say, hey, you gave me completely invalid arguments, like I'm not going to run that. um, so in order to get control over the parameters, we use what are called ROP gadgets, and these are um, very short instruction sequences followed by a ret. You can kind of think of this as just a really, really short function. And then we can do the exact same thing that we did um, with our ROP chain with functions, but instead we just put in these little tiny ROP gadgets, which I guess you can just think of as really tiny functions. So, for example, we can do something like this. Where we put a Poprdi gadget right here, and then we put the RDI value above that on the stack, and then we put like the address of system right after that. So what this is going to do is it's going to first jump to this Poprdi gadget, and so that's going to jump somewhere in the code, and it's going to jump to a Poprdi instruction. So it's going to call Poprdi, which is going to um, pop this RDI value off of the stack and store that into RDI. And then it's going to call that ret instruction, because ret was the next instruction, right? Because of the way that we um, found our ROP gadget. Um, and then when it calls ret, uh, or when it executes ret, it's going to return, and it's just going to return to system. So now we are able to call system with RDI set to whatever we want, just by changing this RDI value here. Um, so now we are able to control the parameters that are going into our functions, and now we can start doing really interesting things, like we could pop like the address of /bin//sh into RDI, and then call system, which is just going to um, stop running the current program and replace it with the program bin/sh. So we now have like access to a shell on the remote computer. Okay, so um, you may notice that these ROP gadgets look like they would be difficult to find by just like looking through the whole binary, and there's a tool called ROP Gadget that can be used to solve this. Okay, so that was kind of the like high level overview of a lot of binary exploitation stuff. But now I'm going to actually demo solving some tasks. So I just pulled um, 2 challenges off of Forever CTF that I have not solved. So I will solve them on during the talk for you guys as a kind of uh, um, example in how you do this stuff. So can people see this terminal? Oh, there's a
Yes,
bunch
there
of
was
chat
also a
messages.
question in the chat, real quick.
RDI is the argument we made for system. Yes. Um, and yeah, I am live solving. It's gonna be fun. Um, okay. Oh, I guess the question is like, why is RDI the argument for system? And that's just because of x86 calling convention. It just says that the first argument to every function is always stored in RDI. So system only has one argument, so the argument is stored in RDI. Um, yeah, that's just like a standard thing. It's just like a fact, I guess, that Intel said was true. So now everyone is obligated to follow it. Hold on, I'm going to open this binary encoder so we can so we can inspect it before doing the actual exploitation.
Sorry, I just showed up here from another meeting. Is there somewhere I can download these binaries from?
Yeah, they're on Forever CTF. I
Okay,
think this
thanks.
one's called Jump, and the other one I'm going to do is called ROP.
All right, cool.
Okay, so I don't know if you can see this. I don't know. I don't think I can zoom in. Is this like readable? Oh,
Yeah,
zoom
it's
in.
Cutter,
readable.
you can. It's like control scroll to zoom. I think
Oh, okay. Is this readable?
a little small.
You can
That's
also
better.
make the window smaller and then it'll look like it's zoomed in.
Okay. So um, this is the main function of this jump program. So we can see it just says it loads a string. Haha! I removed the if statement. You can never hack me now. Um, and then it prints that with put s, and then it calls vuln. So we'd probably expect the vulnerability to be in the function called vuln. So let's see what it does. It allocates a stack frame of size 0x70. It loads give me some input into RDI, and then it calls put s, which is going to print give me some input. And then it um, loads this string, which is located at RBP minus 0x70, and it puts that into RDI, and then it calls get s. So we have this same thing as I talked about during the presentation, where we're calling this super dangerous function called get s, and we are able to overflow the return address if you just think back to that picture that I was showing earlier. So okay, what do we want to target in this binary? So I see that there's this function called get flag. So I assume that if we call get flag, it will probably do something nice, and we will be able to get the flag. So essentially, what we want to do is overflow this return address and change the return address to get flag, and then we will it looks like this will spawn a shell for us, and we will be able to interact with the remote server. Okay, so let's go about actually doing this. So I'll switch back to my code window. So um, I'm going to use this library called Pwn Tools, which is like a very common binary exploitation library. Um, And what we're going to do is we're first just going to load the binary. It's called jump. And if I were to do r.interactive here, what this is going to do is this is just going to run the binary, and then r.interactive is going to say, just let me interact with the binary as if it was like running in the shell. So if I were to run Python 3 exploit.py, you see that it starts this local process, and then it's just interacting with the binary normally. Okay, so how do we actually exploit this? So first of all, we know that we need to send r dot send line. We know that we need to send 0x70 bytes at least to overflow that entire stack frame, because the stack frame was of size 0x70. However, we also need to add 8 to this, because we also need to overflow that saved RBP address that is between the stack frame and the return address. So then if we add an address here, this will be what we're actually overflowing the return address with. So if we were to run this code, I guess I can run this code. We expect it to crash because we just overflowed the return address with a 0, which is invalid. So we get a segmentation fault, and that is exactly what we expect. I guess I should mention this P64 thing just turns a Python integer into like a C integer in terms of bytes. So it kind of just turns a Python integer into like the string representation. Uh, as we would kind of expect to see in our program. So I'll use this other Pwn Tools module called elf, which this just loads the binary in an easy way that we can kind of like look up addresses. So we can do something like e.symbols get flag. So what this is going to do is it's just going to look through the jump binary and find the address of this function get flag, and it will give that to me as a Python int, and then I'm converting that Python int to the like C byte representation, and I'm just appending that onto the end of this string of a bunch of A's. So essentially what this is going to do, the first 0x70 A's will overwrite the entire stack frame. These 8 A's will overwrite the saved RBP with a bunch of A's. And then this last value here will overwrite the return address with the address of the function get flag. So if we were to run this now, hopefully I should get a shell. So you can see I can like type ls into it. I can look around at like the programs that are running. However, if I run like who am I, it's running as me. So the problem here is that I've run the binary locally, and I just exploited my own computer, which doesn't really help us at all. We want to exploit the remote computer, right? Because we're interested in stealing whatever like corporate documents off of their computer. So let me look up the uh, actual address here. So this remote function is just going to do the exact same thing, except instead of executing the binary locally, it's just going to connect to the port 1303 at forever.ieees.io, and it's going to expect that to just be like running the binary. So if we do this instead, you can see that I now am on the CTF machine. If I type in who am I, I'm running as the user jump. I'm not going to print the flag because maybe you guys want to solve it yourself. But I've now successfully exploited the remote server. Okay, so that was jump. That's kind of like the exact same exploit as was talked about in the talk. And I want to talk about one more, which is called ROP. Let me open this in Cutter again. ROP. Okay. I think it's opening. It's taking a while to open. Yeah, okay, it opened. So let me zoom in again. Okay, so this one took a while to open because I guess it's statically linked, which just means it contains a bunch of other functions rather than just having like main and whatever was written. But it works the same way. So let's see. So we call main allocates a stack frame size 0x40, and it prints, hey BB, what's your name? And then it asks us for input into the string s, and s is at RBP minus 0x40. And then it looks like it will then print hey, and then whatever we put in there, and then it's going to say see ya. So again, we're calling get s, so we were able to do this overflow the return address thing. And instead of 0x70, we now need to overflow 0x40 bytes. And now the question is, does this binary also have a get flag function? And it looks like it does. However, the get flag function looks significantly more complicated. So let's see. The get flag function now takes 4 arguments, and it looks like it compares the first argument to 0x1337. If it's not 0x1337, then we just return. If it is 0x1337, then we compare the second argument to Cafe Babe, and then if we if the second argument is Cafe Babe, then it compares the third argument to Dead Beef, and if the third argument is Dead Beef, then we call this code down here that actually gives us the shell. Okay, so we'll have to use a little bit of ROP to do this, because we need to control those parameters, and I guess this is kind of hinted at by the function or the program name of ROP. So let's run ROP Gadget on this thing, and let's look for Poprdi. Oh, I need this in parentheses. I assume this is taking a while because this binary is really big, so there's a lot of ROP gadgets. So there is a Poprdi ret gadget here at address 0x4018ca. Instead of doing this for each address, I'm just going to do this in Pwn Tools. There's handy from Pwn import star. There's a Pwn Tools module to do this this ROP gadget lookup thing for you. So this is called ROP, and we do the same thing where we load the binary as an ELF, so we can look up different addresses, and then we use this ROP module, and this ROP module allows us to do things like Poprdi equals ROP.find gadget, and then we could put like Poprdi ret, and this will find us the like first Poprdi ret gadget in the binary, and we need to do this for we needed 3 arguments, so RDX, RSI. So this is just again calling convention. So the first argument is always passed through RDI, the second one is always passed through RSI, and the third one is always passed through RDX. So here we do essentially the same setup as before, where we did, I'm going to write this as payload. I'm gonna kind of make it easier to read. So first we need to overflow the entire stack frame along with the saved RBP. So that's 0x40 plus 8. And then we are going to start constructing our payload. So we want a Poprdi, and then we wanted 0x1337 here, and we're just going to do this for the all 3 of these arguments. So RSI, RDX. I think this one was Cafe Babe, and this one was Dead Beef. And then we're going to call get flag. So what this is going to do is it's going to do a ROP chain, and it's going to put 0x1337 in RDI, Cafe Babe in RSI, Dead Beef in RDX, and it's going to call get flag, which should give us a shell.
So you didn't define get flag.
Oh, yeah. Thank you. So we need to do e.symbols get flag. And that's again just getting the address of this get flag function from the binary. And then we call r.interactive, and this should give us a shell. Python 3 exploit 2.py. Cool. Yeah, it gives us a shell. I won't run this on the remote thing just for like time's sake, but it would be the exact same process as we did on the first one. And I just realized that there's a interesting unexpected solution for this problem as well. So I'm looking. I think I switched back to Cutter. Hopefully, me. Yeah. Okay. We're back on Cutter. So notice that if we were to skip all of these instructions and just start executing here, that we would still get a shell. The only thing is that we need to write to these like var 10h and var 8h addresses, and those are calculated based off of RBP. So the problem here is if we were to just jump here using the exact same exploit that we had before, RBP is overwritten with a bunch of A's. So when it tries to write to this address, it's going to try to write to a bunch of A's, which is not a valid pointer. So the program is going to crash. However, if we just overflowed the saved RBP value with like a writable memory address, then things would be fine and everything would work as we expected. So let me do that real quick. So I'll just copy exploit 2 to exploit 3, and okay, so the difference here was that we need we only overflow the stack frame, and then what we need to do is we need to put a writable address here. So there's a thing called BSS, which is just always a writable address in any binary. Don't really worry about like why it exists, just know that it does. And then let me copy the address. So we wanted to jump to a specific place. I'm having difficulty copying the address. Hold on. 41E31. So instead of jumping to get flag, we want to jump to the middle of get flag. So this is 0x40 13E1, I think. No, 41E31. 1E31. And if we run this now, we don't need to do our ROP chain anymore, and we can just kind of do the easy exploit that we did on the first one. And yeah, it still gives us a shell. Nice. Okay, that is all for the demo. Hopefully that was instructive. I don't know if we're still recording. Are we still recording?
Yes.
Okay. Okay. I guess we can stop recording and then take questions now.